Okay, so we've got machines, we've got dynamics, we've got statistical mechanics, and we've got evolution. And now I'm going to just tell you what complexity science is. It's this. It's everything that lives in the space bounded by those principles. What it is it's some set of principles that help us to understand problem-solving matter. We don't study ordinary matter at SFI. And they can be markets, they can be minds, they can be machines. It doesn't really matter. And if you study problem-solving matter, there are just concepts that are relevant. Efficiency, scaling, robustness, resilience, intelligence, inequality. You know, how is it that they have people coming talking about single cells and genomes and economic inequality and machine learning? What the fuck is going on? What's going on is that those are the right concepts to deploy when you're working on problem-solving matter. Because you don't want to go and sit down and say, what do you work on? You say, well, I work on, you know, the non-linear dynamics of evolutionary systems using non-equilibrium statistical mechanics and the theory of computational complexity. And this is a table taken from The Complex World, the book that many of you should have bought out front. And you can just sort of see, starting in the 40s, this effort to try and come to terms with what this thing is. Dynamical systems with active or purposeful behavior. Hayek's work on sort of decentralized problem solving by markets. And on it goes. And ending with people like Varela, Maturana, and Uraby, on where it's kind of almost not a helpful definition. Unitary and autopoietic organization, recursive networks of unitary processes supporting mechanisms of self-production, non-determinant elements, and so on. This is the first use of the word complexity science. That's in 1948 by Warren Weaver. It's not a new thing. It's not a SFI thing. It's much older. Problem-solving matter produces or contends with this idea of emergence. Andrew Wiles, who proved the Fermat conjecture. But the point about the proof is it's entirely made in a mathematical language. There is nothing to be gained by looking at his brain. The fact that he chose to work on that problem has something to do with his brain. And if he didn't have a brain, he couldn't have proved the theorem. But the correctness of the proof has nothing to do with psychology or neuroscience or any other field of science other than mathematics. It also has nothing to do with economics, how much he was paid, or the market for mathematicians. And it also has nothing to do with who he was trained by. All of those would be interesting exercises in themselves to understand something about Andrew Wiles, but they don't bear on the correctness of a proof. And what this tells you is that mathematics is truly emergent. Phenomena that are not emergent have to be explained by lower level mechanisms. Imagine this at the lower level is the biophysical level. This might be the level of his brain. That brain is operating according to a set of basic rules and principles. And out of those rules and principles comes mind, and mind manipulates mathematical symbols using some logical system. And the key point about emergence is that, as I said before, to understand the progress of the mathematical concept, you don't have to look at the lower levels. They're making progress too. Andrew Wiles' brain is also changing in time, but it's not material. And there are very good reasons for that. And in our field, we call those mechanisms of protection. What makes it possible to ignore lower levels? Somehow they're screened off from the phenomenon at hand. Now, within this framework, Voltaire and Châtelet were emergentist. They were saying, yes, there are rules of physics. And if you're making physical measurements, you need to know them. But if you're making measurements at a higher level, even though they're operating, they're not material. Leibniz was a reductionist, and within this framework, this is what that means. It means to understand the temporal evolution of every level, every hierarchy of phenomena, the only real way to understand their evolution is to look at the most reduced level. If I want to understand things like consciousness, I really have to understand physics. Everything else is an epiphenomenon. This is a manifestly false statement, and the reason I gave the mathematical example is because I think that one's incontestable. So that's a bit on emergence, right? Emergence is this interesting phenomenon where different levels appear supported by mechanisms of protection that allow explanations to be provided that are equally rigorous at almost an infinite number of distinct levels. So that, come back to this, kind of profound, because it means that poetry, operating according to its own rules, is every bit as rigorous as mathematical physics.